the day with a very interesting talk. One of the three people who came from PNNL, Mohantaj Halapanava. He is someone I know for a very, very long time. We go way back when he was doing his PhD and I was a postdoc. And we work in similar areas, high performance computing, graph algorithms. And like many other people, we also went on into doing AI and machine learning. And he has done plenty of that at PNNL. He's the group lead for their machine intelligence. They don't call it artificial intelligence, machine intelligence. I never understood why they're called, but it is very intriguing. And so he will be talking about something that would follow up on these things, but slightly different in terms of graph connections, which I'm very excited about. And so without any further ado, Mohammed, take the floor.
Thank you very much, Hassan. So I think Dave was asking, why did I come here? Just to see you. Yeah, I think we go a long way back. And before I actually went on to do graphs, I was doing cybersecurity, public key infrastructure. And my motivation was because there was a very beautiful Indian movie. And the hero was a crypto analyst. So I reached up and I said, hey, my professor asked me, what do you want to do? I want to be a crypto analyst. He told me, but you don't do any math, cryptography. Let's do public key infrastructure. So that's how I did a little bit of cybersecurity, and then I was like, okay, this is very boring. Let me do graphs. So it was fun for a long time. And of late, I think this work is already 6-7 years old. So we've been doing this for a little bit. And the big idea is that, okay, we are going to give you a sort of a framework, right? So going back to what Dave mentioned with the cuckoo's egg, and it was a very funny way how they actually caught the virus, right? So they saw a discrepancy of 50 cents in the printing costs. And the person who was in charge at Lawrence Berkeley National Lab, one of the national labs, started digging. So why is this discrepancy of 50 cents? They did not let go, and they found that somebody was sitting there and using their computer system to hack into other systems. And so it's a long chain of events that triggers one to one and so on. And all of this needs a lot of information. And that information needs a framework. Right? So I think it was you who said that I want to write bug-free code. I think that's where I start. So if debugging is the art of removing bugs, then what is programming? It is putting them in the first place. Right? So there is simply no such thing as a bug-free code. You may write whatever you want, but there will be a way of exploiting it. So the first principle is treat everything as vulnerable. Right? So everything is vulnerable. It's if not today, tomorrow. You may have the best intentions, but it's going to be exploited. And so that's Edgar Dijkstra is a Turing Award winner. So if you're in computer science, you would have heard it, the shortest path algorithm and so on. And the next thing I think, we were thinking, so why is that we do any of this, right? So why is that we do any of this? I'm not sure if you have heard about this beautiful Indian story. Not us Indian, but different Indian story. So grandfather is telling this tale that within us there are two types of wolves, and they're always fighting. And so one wolf stands for all the bad things in us, like the evil and the greed and so on. And there was the good wolf. And after a little while, after thinking, the grandchild asks the grandfather, "So which wolf wins?" Right? And the grandfather says, "The one that you feed." If you feed the bad wolf, it's going to win. If you feed the good wolf, it's going to win too. Right? So our goal is to actually feed good information to cyber defenders. And you are sitting there, Joe gave this very beautiful, broad plan how to win this war. Yes. And Mike Tyson said, okay, everybody has a plan until they get punched in the face. So now your plans are off. So what are you going to do? I think we want to minimize the time between a vulnerability is discovered and when it can be fixed, right? So what happens is that there are a lot of zero-day threats, and people actually pay for them, and they hold on to them, and so they are not disclosed. They can't be fixed yet because it's a secret, and they unleash them and they want to make use of it. And Joe talked about the Log4 shell. So it was exploited 40,000 times in the first 2 hours, and almost 1 million times in the first 3 days. And so you better come up with some solution in the first hour, or in the first day, or in the first 3 days before everything gets exploited, right? So how do you minimize this? So it needs a lot of systematic information because these advanced persistent threads are very long and they need a lot of different techniques as well. And the talk itself is sort of three broad phases. So what is the information that will go in, and what are the tools that we are going to build, and what are the insights we are going to get? It's a very simple system. So what is the information we are looking at, right? First part, the very first set of information that is available to us. So this sort of goes back about 3 decades now. And Mitre came up with this beautiful idea that if we all have a common language to express vulnerabilities, and so then it would be good, right? So we can all talk with each other, right? So bugs, I said, okay, there's simply no way you are going to write any bug-free code. It will be exploited. So in which case, a bug, mistakes happen not just in the code, but also in the design and the hardware and so on, and protocols and so on. So if there is a bug, it's fine until a bug can be exploited, right? So that's when it becomes a vulnerability. What is not exploited, it's fine. But if it can be exploited, it becomes a vulnerability. And through this, yes, sir.
What is the map on the right? I guess you didn't get to it. What does it mean?
Oh, which one?
Oh, I guess it's the map on the right. It's got a key underneath it, but I can't read it.
Oh,
He's asking about the map.
oh, the map. Oh, this
Yeah,
map, right?
yeah,
Yes.
yeah.
Yes, I'll come to it. I'll come to it. Thank you. All right. So if a bug can be exploited with some tool, right? So it becomes a vulnerability, and then you can make the code behave something that it was not really intended to do. It's a simple web browser, but now you make the web browser exploit into your own system, right? So you make it go to a lot of these other things. So that becomes a vulnerability. And once a bug is determined, it can be determined by a lot of people. It is then put in a common registry where the entire world can know about it. And there are about 457 different authorities that can now publish these vulnerabilities, right? So Microsoft is at number one because they write a lot of code and they have a lot of bugs. So next would be somebody like OpenAI or Cisco or NVIDIA, because those are the ones. And that map basically shows that these authorities are all across the world. Once you become an authority, you can now publish this vulnerability in the database. And the database is really available for anybody in the world to use. And now, because it is available, people can write mitigations to it, right? They write patches. They tell you how to go fix it. So it becomes a way. And some of these examples could be like it's a broken authentication. It is SQL injection, which is very common. Let's say you have a sequential, like prompt injection is like a predate to prompt injection. There was a SQL injection. You make this query, you make the database behave something different. And then there is the cross-site scripting and so on. So there are a lot of these vulnerabilities now. So vulnerability is very specific to a product, right? So SQL injection may only work for PL SQL or Oracle server or so on, right? So they're extremely specific to a given product. But there is a general dictionary of these called as weaknesses. So that provide you an abstract sense. Right? So given vulnerability is of a given specific type of weakness, and it can go into multiple areas. So for example, we talked about the SQL injection. So now the weaknesses themselves are organized into a hierarchy. So there are about 1,000 or so of them. And the deeper we go within this hierarchy, the more information we are going to get. Yes, at a very high level, okay, it's just improper neutralization, but we can keep digging, right? So this is improper neutralization of special elements. Right, into a task, and we can keep going further. Right, so now we are getting into these SQL injection kind of things. So the deeper we go in and we map, the more information we are going to get. And these are completely independent of a specific product, right? So this particular SQL injection would be applicable to all databases very broadly. And if we develop some kind of a mitigation approach for some of these weaknesses, we get a lot more insight. And the immediate ask is, can we map a given vulnerability to a given weakness or a set of weaknesses? And so that becomes a big task. As soon as I know a new vulnerability comes in, if I know which weaknesses it's going to be mapped to, you'll get a plenty of information, right? So because you might have already seen a lot of these weaknesses being exploited before. So it gives you a lot of this information right away, but not much exists in the form of these maps already. And so very few of them have been mapped. So MITRE is the one that introduced all of them, and that MITRE has actually mapped less than 2% of the map vulnerabilities already that exist. As it's human intensive process. And the question we were trying to ask is, can we automate this process? And it came about in a very weird way. So we had a visitor at PNNL, and we were just sitting and talking, and I was telling him about the metaphor comprehension work I was doing in natural language processing. And then he said, oh, there is this kind of idea that if we can map these two things, they are both text. If we can map them, it would be very helpful. And it turned out, we had to wait a few more years until LLMs came before it actually became useful. And so the technology was not ready. But then that was the idea. So we have vulnerabilities and we have weaknesses now. And this is still all on your side, right? So as a defender, this is what exists on a given system. We have not ventured into what happens on the attacker side. And before we know, I think this is what we wanted to do. We try to link with a smaller set of CWEs. So that's just our work, but it's broadly applicable. And what we also found is that a large class of them have been mapped, but they belong to very few classes of CWEs, weaknesses. And a lot of them, there is simply no information for us to actually train. Supervised training is the easiest one. It's the most stable one if we can find it, but it also needs a lot of ground truth information for us to actually do something effectively. But the ground truth simply does not exist in this case. So that was the one. So now moving on to the attacker space, right? So now there is the bad wolf into picture. So how can you exploit a given vulnerability that is called as a KPEC? It's written again in a MITRE established this database. So they came up with this very nice way, a common language where people can write about it and people can understand and put it in a common database. So these attack patterns tell us how to go step by step and exploit a given weakness. Okay, so they are still in an abstract sense. They are not very specific to a given product and things like that. And we can instantiate them and see how we can actually exploit a given vulnerability, right? Vulnerability for a Mac is a specific vulnerability, but Mac, Windows, or anything else, it's in an abstract sense would be a weakness. So KPEC could be a similar analogy there. It's a little more abstract, but these KPECs are also application specific. Right? So very specific to a given application could be like SQL injection. How do we exploit the SQL injection, or a session fixation, or click jacking? How do we do this click jacking? So it's very specific to a given application, but they can also be abstracted out. Right? And now if we can connect a vulnerability to a weakness, and then weaknesses are connected to KPECs, right? So then we are getting a lot more information. As a defender, you not only know a lot more about a given vulnerability, but you also know how people are going to exploit it. Now you can start thinking about how you are going to mitigate these exploits. So that's what happens. But there is also something very nice. Dave showed you about the Atlas metric, which is specific to LLM, but this is actually the attack framework. And attack framework, think of it same way. So KPEC was very specific to an application. So now attack framework is general at the broader sense, at a network level. And now you can actually see how you can span across for an advanced persistent threat. And so you're not going to suddenly hack into somebody's system right away. You first do some reconnaissance, right? What kind of users are there? You do some social engineering, and then you get onto their web server or somewhere they first let you in, and then you do lateral movement and escalate your privileges, and then you're going to do something, and towards the very end comes the payload, right? So you want to steal data, so that's what comes at the very end. So broadly, there are tactics at the higher level. So what are these big tactics? Like groups of goals, and then for each tactic, there are a set of techniques and procedures which will tell you exactly. So now we are getting specific. It's if you want to do SQL injection for Oracle servers will give you a set of these procedures. And so they are getting a little more specific, but you are not going to do SQL injection right away, right? So you might have to do a few steps before. So you will get a broader sense with the attack. So this is all of the information that we have. And if we want to build an effective framework, we want a mechanism to actually connect all of them in an efficient manner. And once we connect them, we also want to be able to query the information. Right? So I have complex information now, all linked with each other. I want to be able to also query. And what we will discuss now is, okay, how do we go about building this set of tools? So LLM was good. It was both the source and the target. But now for us, it's a tool. And so we use LLMs to actually build these maps. And one of the best parts for us going into this work is that the vulnerabilities, the weaknesses, the CAPEX are all written by human engineers, written really, really well. So they are short, very brief, but they are well-written text. And the data set itself is very clean. It's very usable for LLMs. It's not noisy, it's not messy. But one of the big shortcomings is that there's very little groundwork information for us to do supervised learning in a way. Right, so next we'll go see how we can actually make use of all this data, right? So our tool was the LLM, and so we do have a linguist here. So what is the meaning of a word? Right? So it goes back more than 70 years ago. So Firth basically observed that you shall know a word by the company it keeps. And so we are still using the same concept. And so the meaning of a word is in the neighborhood of this word. So what other words is it being associated with? And all the language models in some way are trying to capture this essence. And so that's the insight. If I want to know one CV, what is the meaning of this CV? Okay, what other CVs is it associated with? What other weaknesses is this associated with? And there were a lot of techniques that came in. Some of the older ones were basically saying in the semantic space. So how do we build this Euclidean space for words and for documents, things like that, or for sentences and paragraphs, right? So you basically do eigen decomposition and we look at the space, right? So we take a given text, we embed it in some space, geometric space. And one of the first tools that made a lot of impact here was word2vec. You've given a word, we can embed it into a vector. Given a line of text, we can embed it into a vector. Given a document, we can embed it into vector. And which was more or less revolutionized with the invention of the attention model. And one of the first implementations of it was BERT, right? So doing bi-directional encodings, and that led to a lot of the modern revolutions in LLMs. Right? So this is the very fundamental building block. And the whole idea is, okay, I have a lot of neighboring words. Where am I paying attention to? So that's what it is learning. And so given a small thing, it'll encode everything, and then it'll pay attention to what these encodings, and then it'll start doing the decoding. Right? So, in its simplest form, a language model basically just predicts the next one. If I keep doing this in the chain, you can start producing sentences, you can start producing documents, you can start producing poems. So whatever you want. Right? So the attention model sort of learns all of this. And what we created was this Siamese model, right? So on one side, you would give it the CVE description, and on the other side, you would give it the CWE description. And there is a security text. It is sort of that is common to both of them. But our goal for learning is, can it predict if this vulnerability is linked with this weakness? And so that's the learning goal. And then we have this reconstruction decoder, which basically sort of learns from the link predictor as well, right? So the link predictor, you can give it anything you want, right? So we gave it BERT, and we can give it any encoder models. And we can also give it decoder only models, right? So we can play around with different models here. But the learning goal was to see if we can accurately predict. And so how accurately can we predict? We have enough information to actually start doing, right? And the link prediction engine is going to tell us how do we optimize these parameters for. And this is still a little bit of an old school, and we don't want to do this anymore because the language models have become extremely bulky in a way. And if I touch it and next in 3 days from now, there is a new fancy language, we'll be stuck with whatever we had edited. And so this model is not going to do very well. So I'll come back and show you a little bit more that we did afterwards. And this was our first work. Right? So we had to wait a little bit to move from the latent semantic analysis kind of technology to the BERT kind of technology, right? So the encoder technology before it actually worked for us. And we published this somewhere around 2021, which already feels like 5 decades ago. Right? So this is LLM, it moves really, really fast. Right? So, and it actually won the best paper award in one of the AI conferences. And for our implementation, we basically started using Hugging Face was still new. And PyTorch Lightning actually gave us significant speed up for performance. So PyTorch Lightning was very important for us. And so now we were able to scale it across GPUs. We were able to make better use of a given GPU and so on. And again, please see this as something that's almost 5 years old by now. So we're still doing a lot of things by hand, all of which has gone away by now. And what we also did was to see, because like Asifa said, I also have background in high performance computing. We were wanting to see how does it scale across GPUs, right? So we are going here from 2 to 16 to 8, different generations of GPUs. Right, so now there's Blackwell, which is even faster than this, almost 2 to 3 times faster for language. And we are also trying and experimenting with a lot of different language models. So there is just but all different variations of encoder only models, but we are trying with different models as well. And what we observed is that some of this is actually compared with the state of the art at that time. Right, so the only thing we could compare against was the TF-IDF model, which is the term frequency and document frequency kind of model. And what we were observing is that here 111 basically means what is my top, right? So you're only predicting the top one, and 3 to 1 basically says I'll pick 3 at the top level and 2 at the top level and 1 at the bottom level within the hierarchy. Right, so if I'm predicting 3 as my answer, I'm going to increase my accuracy instead of saying, okay, I'll only predict 1. Right? And in this part of the chart, we are showing that the data is really, really small. And so we basically do not have enough information to train. So it's just it's flying blind in a way, what is called as a 0-shot or a 1-shot learning, few-shot learning. And here we have a lot of data to train on the right-hand side. When we have a lot of data to train, the model does really, really well. So almost 90-95% accuracy. And here our accuracy was a subset of the data from the NIST database, National Vulnerability Database. So that's what we were testing against. And B2W BERT is our model. And all the TF-IDF, you see the blue ones and the orange ones are previous state of the art. So both green and red are our one. And we started seeing that when there is little to no data to train, we are doing really well. And when there was a lot of data to train, I think any model would be a good model at that point, because the deep neural networks sort of make all these associations very nice. And then we have only limited set of data, right? So we are not throwing it. And we also try to do this between time, right? So we would block from beginning to 2017. And so that's all we use for training. But then in our test, we start testing from 2018. So it is seeing new things that it has never seen before. And every few years, the language for vulnerabilities and weaknesses changes. Right? So because the type of attacks are changing. So there is a constant flux in how people exploit. There are new products, new tools, new techniques. Everything is being developed. So we do see quite a bit of improvement. Again, if you want to predict only 1, so it's always harder, the blue line. But if you are allowed to predict more than 1, right, so as a cyber defender, you shouldn't really care, right? So I'll give you 2 options. So you can pick from 2. You can afford to have better accuracy. And the next was so now we have mapped vulnerabilities to weaknesses. So now we want to map weaknesses to attack patterns. So here the problem was even worse because there was even less data for us to train. And so the lack of information is what was hurting us the most. And again, one of our first approaches was to again use the Chinese kind of models. Right? So we do the CWA on one side, we do the KPEC on one side, and we try to do the link prediction. And so link prediction task basically says, okay, is this vulnerability the right fit for this weakness? That's the question. And the other approach, we used what was very new at that time. They are called as the sequence to sequence models. They'll take a sequence of words as input and they produce a sequence of word as an output. And so T5 was one of the smallest ones from Google. It was state of the art. And now you can sort of do like you're beginning to see the prompts. Right? So in the first line, we basically ask, give me one weakness to attack mapping. And you give it a weakness description, CWE 20, and it picks KPEC 10 as the predicted attack pattern. Right, so and then you can ask, give me two weaknesses for a given attack. It can predict two. Or you can also ask it other questions like, what is the weakness? This weakness is a child of what weakness? It can give you the proper ones. Or also, you can ask about attack model. So with this attack is a child of which attack? Like for example, buffer overflow. It will give you some response. And the trouble with LLMs is that it is always going to give you a response. And the more you ask, the worse it gets. But that is the whole idea, that it will never say no. It will always come back with some response. So you'll have to see how you want to make use of that information. And what we observed is that both the tools were doing really well. And so there were some changes here and there, but more or less the top hits were going on really well. And we published this in 22. And this actually also won one of the best paper awards in a conference, Homeland Securities. And we had only one cybersecurity expert with us who went to Amazon Web Services afterwards. But he was handpicking and doing this manually and giving us the ground truth. So it was very small amount of information. And the second set of approaches we have, the second set of tool, which basically was on the title of the talk, was to see if we can do graph RAG. Right, so it's one of the latest developments in language models was the retrieval augmented generation. So what it means is that the LLM can create an output based on your query. And sometimes it gives you a really bad answer because it does not have a lot of context. So, but the technique here was that, so what if I actually augment some very relevant data along with the query? So now the LLM has a lot more to tell you the response. Right, so I'll not only give you my query, but I'll also give you all the descriptions of the vulnerabilities and weaknesses. Now the language model has a lot more to come back with a response. And this sort of revolutionized a lot of it, especially in medical science, things like that. And so you don't want to give wrong information to patients or to doctors. So this revolutionized the retrieval augmented generation revolutionized. And one of the modern trends here is with graph retrieval. Right, so what I'm querying is not a database, but it's actually a graph, because we had this complex information, right? So we have mapped everything. We have vulnerabilities, weaknesses, attack patterns, and network attacks, and so on, tactics, techniques, and procedures. So all of that we posed as a knowledge graph, and now you can ask a question, and then it finds this nice way. Instead of SQL, we basically interact with this using CySER queries. So this is from Neo4j. So if my data is in the Neo4j database, I can write CySER queries. I'll come and show you a small example. CySER queries, and you can extract the relevant information, give it to an LLM, and then the LLM will give you a response. I think this point came up a little before. So I just took this image from somebody, but they definitely have the right intuition here, right? It's a parrot. So the first criticism for LLMs was their stochastic parrots. They just regurgitate whatever they have been fed, right? So they just mimic whatever they have been taught. They don't really understand. But the newer versions have some reasoning built into them, like the O3 Mini and things like that. So these are very recent trends with reasoning models. But the first few generations were all basically doing them, but stochastically. So Dave brought it up. You can ask the same question 10 times and you'll get 10 different answers because of the stochasticity. And into the deeper model itself, that because we have these randomized matrices, bias matrices, so there's a lot of randomization that goes in. So that's the insight. And with the Neo4j CySER query, you can basically ask it to give me what all the weaknesses or attack patterns associated with a given weakness or a given vulnerability. Now you have a very nice way of extracting the information, assuming you kept the information in a good way. And you can also start asking these more complex queries. And so you can go from vulnerability to weakness to attack patterns and then to attack mechanisms. Right? So you can ask these complex queries, step-by-step queries. So that are usually very hard for language models to come up with. But now we have a systematic way of querying and giving it a better context. And the CySER queries basically look something like this, very simple in their construction. You say, okay, this is my path, go from this CVE to CWE to KPAC, and then come back with the results. And then you want them to be ordered with certain path length or things like that. They have order by, and you can also say how much you want to see. And so you can say, I just want to limit to 10. I don't want to see another 10,000. So it looks almost like a SQL query if you have done SQL querying. It's very similar. And the new advancement there is that you don't even have to write all of these queries by hand. So there are beautiful tools, and again, you can use LLM to do text. You write it in text, and it can basically convert it into a query like this. And so the prompt there was like, what are the possible attacks related to CW89? It sort of converts that into a CySER query. You run it against your database, and you come back with the response, and then you see how different is this answer now. Right? So for insights, we basically say, so this was our first simple example. Find the CAPEX related to CVE 2021 34527, right? And so this is Llama 3, which is still one of the state-of-the-art LLMs. It's like from Meta, and it is equivalent. And we try to use open source ones. And it's basically telling you currently there are no CAPEX associated with it. That's what Llama is telling by default. And we run it through our mechanism. It's still the same input from the user, and it comes back with more information. And because GraphRag has this context, it can go extract this information, and it has a systematic way of doing it. And it can also give you why it is telling you this response. Right? So it's also giving you this detailed explanation about each of these CAPEX. And so another example. So you basically ask it, tell me about the impact and exploitability score of the CVE 1999-009. So they basically give you the year and the sequence in which they came. Right? So this vulnerability was announced in 1999, and that was its number. So the Llama 3 basically tells us that the exploitability score for CVE is low. Right? So that's what Llama is telling us, because it does not know any better. But now we can do the same in graph query, and we have the exact information that we can extract. And it comes back with a score of 10. So this is as high as severity goes. And so if you are a cyber defender, and if you are told that it is low, you basically means that you can ignore it for now. If it is 10, you better go do something right away. And so that's the difference. And so that is the difference you want in your tools between not ignoring something versus doing something right away. I think that's the beauty of this tool. And we also built these other tools. And in fact, one of the WSU teams came and they did a capstone project with us. So they have done a really beautiful tool for us. I don't have the screenshots for them, but this was a simple tool we built for our own cyber users. So which gives a very nice view of different CVEs. And then now, because we can also link a given CV with a CWE, and we can also use these word embeddings to cluster. Right? So what other vulnerabilities are in this area, right? So there is a new zero-day exploit, and you don't know anything about it, but you can, if you know that all these other things are also exactly like that, so now you can go actually do something about it. So this tool gives you a nice and user-friendly way of looking at all of it. And some of the use cases I was sort of digging into was to see if Microsoft Office corruption is a very popular vulnerability, right? So CySER had announced it. Okay, this is one of the top ones that is routinely exploited. As everybody wants to exploit this because it was there, and you can get more information right away by looking at the CWE, and because the CWEs are also mapped with attack patterns, you also know how people are exploiting it. Now you can go deploy the tools to patch it, prevent it, and go do whatever you want to do. And these were some of the top ones. And we can look through all these different schemes right away. You can also see what are these clusters. Okay, CW 119 is also coming along with the CWE20 and these other weakness classes together, right? So people are not just doing one thing at a time, but they're doing multiple things. And so there is a very neat way of looking at all of this. And we also had the severity scores, right? So most of them are in either 10. So anything 7 or above is very severe. So anything 5 or below, I think I might be misstating it. I'm not a cybersecurity practitioner per se. To me, they are just numbers, but higher the number, the worse it can be, right? So very severe. You want to do something about that. Excellent. And a lot of these other schemes. And we also built this KPEC Explorer. You can sort of start anywhere in this chain, and you can go left or right, and you can extract all this information in a neat manner. And just to conclude, so ours was the first work into mapping CVs to CWEs using LLMs. So we used the power of large language models at that point. But we also connected CWEs to KPEX, and KPEX usually have some connection directly into the attack models. And in the graph rack system, we have connected all the way through in the knowledge graph. So you can go back and forth from any direction you want. And this was also made possible because we sort of created this interesting signings network and doing the link prediction. And we also scaled it to V2W BERT because we could use larger language models. They have more context, better accuracy, and so on. And we also were trying to do this as a multi-class hierarchical classification problem. It's a little harder problem per se. And we also can have multiple labels, so that it sort of gets into the more difficult range in the classification problems. The knowledge graph that we have built, again, it sort of assumes that all the information that we are putting in is known and it is solid information, but that may not be the case. So for the coming summer, we are trying to make sure that we can also do this knowledge graph completion task, because it's an infinite space almost. How can we not keep everything in the database, but it sort of predicts on the fly? And so the language models are extremely capable now, and we can do this language graph completion. You don't have to keep everything in time, but it can go and come back with confidence numbers and so on. And the other idea is that we did as researchers usually in isolation from ourselves. So it's great that I'm getting to work with Joe a lot more. And so we usually go into our own remote corners as scientists, and we do whatever comes to our mind. But we're looking forward to work with subject matter experts and see actually they can make use of these tools, right? Are they just done in isolation and nobody cares about them, or they can actually be used in the day-to-day cyber operations? So that's where we are going. And again, one of the concluding thoughts, I think it was great to have Dave's talk right before me, is the language models are getting extremely big. Right? And then you plug in one model into another, and then you make combinations of those. You plug it into some other model, vision models, multimodal models. I'd say you plug in one vulnerability in one of them, you break all the hell loose, right? So we are looking at a tsunami of AI disruptions, and cybersecurity is one of them. Right? So what really hurt me as an individual is to read this one book on ransomware attacks, where lives of common people, and so were destroyed because of ransomware attacks, right? So they are attacking hospitals, they are attacking your utilities, they are attacking individuals. So you are a photographer and your system is locked. You can't earn your livelihood because all your photos are locked in. And so, so what you are going to do next is of great importance. Okay, you're funded from DoD, but okay, that's one. But you look at all the people, right? So there is huge agricultural community here. So it can get locked down. And so they are farmers, they are not interested in cybersecurity per se, are not capable of doing it. So it can have huge consequences. And we are not prepared for any of it. And we don't even know if we have even understood what all this means. I think that would be the conclusion.
Thank you very much. We have time for questions. We will have time.
open up for anybody.
Yeah, we'll update the titles we use because all three of you had fuller sounding titles now than the titles we have had. The titles for the talks is what I mean. They had always cool titles for themselves. I meant for the talks, right? And we will update them. If you have questions, I think we have some time to ask, and it could go to everyone, right?
So I was wondering if you, through your analysis, saw any specific areas that had like a higher occurrence of CVs, like in legacy systems, or like you were talking about, is it gonna be like AI is gonna create a lot more like in the future?
Yeah, I think we already have quite a bit that is exploited. And so AI is going to create more because that's how most of our applications are going to go. And so we are not using the old tools anymore. We are just replacing the application tools. But we'll continue to use all the old tools and they will have all the old vulnerabilities. And we had a guest lecturer one time said, if you think software vulnerability is huge, that's why I said, okay, there are close to 300,000 vulnerabilities now. So if you thought software was big, hardware is even huge. So software is just a tip of the iceberg. So hardware vulnerability can also be huge. So MITRE started to do some of this, but then the funding for CV might go away. So I don't know, we'll not have a common language to talk. So it will be both.
Okay, thank you.
Yeah.
I wanted to ask on your slides where you had RAG versus graph RAG.
Yes.
It looked like you just said you were querying directly to Llama or whichever it was. So what's the advantage of using graph RAG versus using vector database RAG?
Yes. So vector database can be anything, right? So vector database in general is primarily used for documents right now. And graph RAG is for graph, knowledge graph in a way. And so we have different graphs of different types and we have these strict relations. Right? I can ask for CV001, what are all the weaknesses? You just walk and then you find the exact patterns out. But in essence, they are very similar. And if you have a big vector database, so the technique there is to see if I can scale it to billions to trillions of these documents and how do I quickly get them and so on. And it's actually stored as a graph as well. It's called the hierarchical small world navigable network, somewhat from HNSW. You can read about it. So it's how do you quickly get into a given space? How do you find all these vectors? So the idea is that you find vectors that are similar in some Euclidean sense, as you look at cosine distance. But they're very similar.
Other questions?
Yeah, also for Dave and
Sure. The questions are open for everybody. I have one question while maybe they think in one of the earlier works, right?
Yes.
You had link prediction.
yes.
And it was a mapping that you wanted to do between vulnerabilities and weaknesses, right?
Yeah.
Are you predicting in the sense you described about how the mapping is done, and because of that you say this is what the link should be?
Yes.
Or is it the link prediction we think in graphs and you're predicting a link there? Which one is it?
So, okay, the terminology might be a little confusing.
Yeah.
Right, so the link prediction also exists in graphs,
Yeah.
where we are asking if a link exists between two specific nodes.
Yeah.
In our case, we don't really have a graph.
Yeah.
What we are asking is this vulnerability. So we have 124 top CWE classes.
Right.
So which one of these 124 is the best match?
Okay. Okay.
But in that sense, it is
Sure.
link
Okay.
prediction.
Yeah.
But
Yeah. I understand. That's great. Other questions? And you can direct your questions to Dave or to Joe. There was a connection I saw in their talks. So there was social engineering, negotiation with LLMs, and then there was call your friend type of thing from what Joe said. And so the human factors, these are great things. And I don't know if you did it by design, but I like where you went with it. And I think it came across through this workshop repeatedly, like cybersecurity has to do a lot with people. So that came through. So great job on the harmony there with the coordination. So that's great. Questions? So I know you can have a seat. I don't know, but I know we are going to have an industry panel on Friday afternoon. It's James might have told you to submit your questions. We know some questions to ask, but your questions should be great. So I think it is today that the deadline is, right?
That's what we're asking for, Maya.
Yeah, so make sure that after dinner today, take care of that. If you have questions that you'd like to ask the industry for next year, I'm going to have this Dave Stone be part of that panel. I think it would be fun. We do this every year. And so now we know what to do next year. So I'm booking now a year ahead for some things. Other things to say tomorrow in the morning, we will go field trip to